Okay, so now we're going to show that read-write memory actually does have these connectivity properties. This is something that you don't often see in math books, for example, because people are happy to show kind of grand principles, but we are going to roll up our sleeves and start digging into actual computations. So before I go there, I'm going to review a yet another classical theorem of combinatorial mathematics called the nerve theorem. The idea here is that if I can take a complex and write it as the union of subcomplexes, then we'll call that a covering. So given a, we want to argue inductively about things, so we want to take a complex, we want to break it down into nice pieces, argue about the pieces, maybe you do it again. So covering is a way to do that. So we define the nerve of a covering. A nerve of a covering is a derived simplex. Each vertex in the nerve is one of the covers, that is one of the subcomplexes. And a collection of these vertexes defines the simplex if their intersection is non-empty. So if the intersection is empty, it's not a simplex. If the intersection is non-empty, it is a simplex. And so given a complex and a covering of the complex, we can get a nerve complex out of that. And the nice thing about the nerve complex is that it typically has a much simpler structure than the original complex. And so if we can prove things about the nerve, then it's better than proving things about the original complex.
Covered by groups of simplexes?
It just says that this big simplex is the union of these smaller simplexes. That's all. So it's a, there's nothing complicated there yet. So for example, here is a sphere which we break into two half spheres. And think of this not as a continuous sphere, but as a simplex that's equivalent to a sphere. And so each piece here is a vertex of the nerve. And the intersection of the two is non-empty, so there's an edge between them. So the nerve of this particular covering is just this edge with two vertices. So what does the nerve lemma say? The nerve lemma says that if I can show the following is true, so if each of these component pieces is individually k-connected, if it has no holes in dimensions k or lower, and the simplex constructed by taking the intersection is k minus size of u plus 1 connected. Basically, what we do is we look at the the cardinality of the intersection and subtract a certain amount for each thing. So the connectivity of the intersections is smaller, and the bigger the number of pieces that are intersected, the smaller the connectivity can be. So if we can show that these things are true, and each one of these, this is a statement about each of the individual components, this is a statement about what happens when they intersect. So if we can establish these preconditions, then it turns out that the nerve looks a lot like the original complex in the following sense, that the original complex C is k-connected if and only if the nerve is k-connected. So if we can establish these preconditions, then if we want to establish connectivity of the entire complex, we can look at its nerve. And the nerve is, as suggested by the sphere example, much, much simpler usually than the original complex. So we basically do all this work reasoning about the components, and then we can put it all together, and then we have one final step, which is usually pretty trivial.
How do you, this is universally quantified on cover? This is for all, for every,
yeah,
for every cover?
No, for one cover. So if you find a cover, you give me a cover with this property, and then it's true. It's not quantified over all covers. So there may be covers where you can't prove the precondition, for example. So then you couldn't apply the theorem. So the
theorem applies, but in a vacuous way.
yeah, 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 yeah. You can't get any useful results out of the theorem,
Yeah.
even though it applies. So no, the nerve is a function of the cover, not necessarily of the complex itself. So different covers will give you different nerves. But if you can find any cover with this property, then you're okay.
So the use is bottom up. So you find a cover, prove the nerve is connected, and you get the.
Yeah, well, actually, what we're going to do is we're going to find a cover, which will kind of arise naturally in the problem that we're looking at. We're going to spend our time basically proving this. You know, we're going to show that this will be true trivially. This will require all the work. The actual nerve is going to be trivial. So all the work that we're going to do in this particular application is in that step of figuring out the conductivity of the intersections.
And is this if and only if, any direction of this if and only if trivial?
No.
Both directions.
No, in fact, we're only going to use the fact that,
Yes.
that because this is k-connected, that's connected, we're not going to use the other direction.
Yeah. But is it interesting or difficult to prove or non-trivial?
I think it's certainly non-trivial in this direction, and I've never actually had taken the time to look up the other directions, so I don't know.
Because if the other direction was obvious, then we could shift around the theorem to
Yeah,
say
yeah.
that this and the two
Yeah.
thing imply the k-connected.
I have a feeling it's not obvious. That,
Because the statement of if then,
Mhm.
if only if is.
yeah. Well, the direction we care about, you know, in the original paper with Near, we actually proved that version of the nerve theorem because we didn't know about the nerve theorem, so we had to sort of do it ourselves. And it's this huge double induction argument. So it's not difficult, it's just you have a lot of subscripts. Example of simple application. So here, remember, we have our covering of the nerve, and each hemisphere here is one connected. You know, you can if you put a string on it, you can fill it into a disk. Each intersection, there's only one, is zero connected, and so. You know, if you check the arithmetic, that means that that's the precondition for applying the nerve theorem. So that says that if this is one connected, then so is this. But this is obviously one connected, and this may be less obvious. So that's an example of how you can use the nerve theorem to do something marginally interesting. Okay, so. Let me define the language that we're going to use for reasoning about computation. Well, a lot of this is not specific to read-write memory. It'll work in other contexts as well. So we'll talk about a protocol state, which is just you can think of it as the program counters and local variables of processes and the state of the environment, you know, in this case, the state of the shared memory. So there's each process, what it's doing, what its local state information is, and what the state of the shared memory is. And this is useful for talking about intermediate steps in a computation, because all the simplicial complexes we've been talking about, we talk about the beginning state, and we talk about the final state, we talk about the views of the computation after it's over, but we haven't really talked about what happens in the middle. So we'll talk about the reachable complex from S. You remember that when you start out, before you take any steps, the entire protocol complex is reachable. You know, it could happen. And each time you take a step, you can think of it as limiting the possibilities. Because once I write a value, then all the executions where somebody read it before I wrote it are now impossible. And so the reachable complex gets smaller and smaller until it's a single simplex, and then your computation is over. So we use shorthand. So given a state S, and we have a process PI that is about to do an operation that is either a write or a snapshot. So we'll talk about that state as S sub I. So S is the state, S sub I is the state if I goes next. We're also interested in the reachable complex from S if PI moves next. And then we'll take, instead of writing this, which gets kind of cluttered, we'll just write it like that. So P sub I is the reachable complex if I goes next. So here's an example of what we're thinking about. So here we have 3 processes, and they're executing shared memory, and we're in a particular state. So this is the reachable complex if 0 takes the next step. This is the reachable complex if 1 takes the next step, and this is the reachable complex if 2 takes the next step. So this is an asynchronous model, so it makes sense to say that they take steps 1 at a time. If this were a synchronous model of computation where everybody steps together, this wouldn't work. But because it's asynchronous, we can say, okay, now, this is what happens if 0 goes first, this happens if 1 goes first, this happens if 2 goes first, and somebody has to go first. So the union of all 3 of these is everything that can happen, assuming there are only 3 processes. Okay, so let's say P0 is about to read some value u from the memory. P1 is about to read this, do the same thing. And P2 is about to write a different value to the memory. So each one is ready to take a step in this state. So let's now say, well, what happens, what about these intersections here? Because if we want to apply the nerve lemma, we have to reason about intersections. So here we have the 2 readers, both about to read. What happens? So if P moves first, it reads U. P1 moves first, it reads U. The intersection of the 2 are all the executions, and think about this for a second, where nobody can tell which one moved first. Because this is an execution where the view is one I could have seen if P0 moves first. It's a view I could have seen if P1 moved first. So it's, this is the one, the execution are all this intersection are all the executions where it's ambiguous which one went first. So we'll say that if S0 and S1 is the state after both of these read, and because they're reading, they, you can't tell which one went first. And so the claim is that the reachable complex here is you go to state S01 by letting them read in either order, it's equivalent, and sort of stopping there and looking at the reachable complex from that state. Okay, well, what happens if we have readers and writers that are competing with each other? So here, P moves first, it reads the old value. P2 moves first, it writes a new value. Here, we can't tell who went first. But the thing is that, in some sense, P2 can tell. We wrote a value, and then it goes on. But P0 can tell because it knows what it read. So what that says is that...
but it doesn't know that it was going to read a U.
No, but if you look at the reachable states, if it's in hindsight, yeah. But what we're doing here is we're saying, well, these executions, it can't be in P sub 0 if it's all the old, if it's all the new state, because then it couldn't have gone first. And so what we have here is that P sub 0, so let's put a superscript up here to say that 0 doesn't participate. So 0 either reads it and crashes, or maybe crashes before it reads. We don't care. So this is a protocol starting from that same state where P0 doesn't participate. So all the executions in S where P0 just crashes, that's the intersection with P2. So what we saw here was that if we look at the intersection of the readers, we have a protocol complex with fewer pending operations because both of these reads happened. And the write is still pending. It's still about to happen. If we look at a reader and a writer, then we have a protocol complex with fewer participating processes. So in one case, the number of operations that are waiting to go is smaller. In the other case, the number of processes that are participating is smaller. So this suggests a kind of an inductive argument, where when we want to reason about the intersections, we'll say, well, this is equivalent to another protocol with fewer processes or with fewer pending operations. And each of those lesser cases will be covered by an induction hypothesis. And that's how we're going to proceed. OK, so just a review before we launch into this. So the reachable complex from S, if Pi takes the next step, is P sub I.
This is something fixed. You fix S.
Yeah, and I'll tell you how to fix S in a minute, but we'll fix an S and then look at the reachable complex from that. The intersection of all of these P sub i's is where it's ambiguous who went first. That's the operational interpretation of what this intersection is. And we're going to prove these things, at least in the notes, all combinatorially. But if you want to really understand what's going on in the proof, then think of it as saying, well, what must happen if it's ambiguous who went first? So we're also going to talk about executions, which is a sequence of process steps, reads and writes. And you know, we sort of dive down when we want to talk about a specific model. We'll talk about executions, and then we'll forget about them. And an execution, at the end of an execution, the views of the non-faulty processes determine which simplex of the protocol complex you're in. If a process crashes, it doesn't appear in the reachable complex, so we don't care what it saw. But everybody who's non-faulty, whatever their view is in the execution tells you what their vertex is. And in particular, if you have you can have two different executions where the views are the same. Either all the views or some of the views. So we'll say that two executions are equivalent if they determine the same simplex. So if you reorder two adjacent reads, for example, no one can tell that happened. All the views will be the same. So those are two executions that that generate the same simplex. Okay, so now we're going to start talking about specifically reads and writes. So here we're getting right down to the nuts and bolts of the read-write model. So I'm going to assume here that all we have are single-writer, multi-reader registers. We could do multi-writer too, but then we have extra cases to clutter things up. I'm not going to assume snapshot. I'm just going to assume you read and write individual variables. Yeah, everybody, you write your own and you can read anyone else's. And we can assume without loss of generality that what you do is you write your own and then you read everyone else's in some order.
And you assume that you write all that you have seen before?
Yeah. So you write everything you've seen. So this is full information.
So at this point of the proof, U is also fixed. You show some U and you consider.
Yeah. So at this point, S and U. Later on, I'll be more specific about which U it is, but I want to build up a bunch of lemmas before we march through the proof. So I'll say that a write in, so we have a set U of pending operations that we're interested in. In the state S, you know, everybody could have a pending operation, but we're only interested in a subset of them, which is the set U. So we'll say by a write here is non-conflicting if nobody's about to read from the same location in U. So that means that, you know, if I write and somebody else does something, nobody can tell what order they happened in because they're not reading. And because we have multi-reader, single-writer memory, all conflicts are between reads and writes, not between writes.
And these are definitions with respect to a single state,
with
respect to an execution, or?
With respect to a single state and a single set U. So in that state, there may be other conflicting operations, but if it's not in U, then we don't care. Yeah, some set of processes that we care about. So the U is actually the set of I that we're going to be intersecting the reachable complexes over. And then we'll say an operation is conflicting if it's a write and there's another reader to the same location in U, or vice versa. If it's a read and there's a conflicting write. Okay, so it's going to be case analysis. So we say that suppose some process PI that's in U has a non-conflicting operation, either a read or write pending in S. So either it's a read or it's a write, but nobody else is doing the complementary operation to the same location. And some PJ has some pending operation X sub J. We don't know what it is. So the claim is that if we look at all the executions where PI went first, and all, starting in S where PI went first, and all the executions in S where PJ went first, that's the same as letting I go first, and then we look at the reachable complexes if J goes first. So this is so we're in the state S, and this says that this is all the reachable states from S where I goes first. This is the same thing where J goes first. Okay, so here I'm going to go from S to S sub I by letting I go first.
You yield to non-conflicting.
Yeah. So Pi has an operation. It's going to do something. So we say, okay, Pi can go ahead. That takes us to this state S sub I. And now I'm going to say, well, what's the reachable complex if I now let J go first? And so what I want to say is that I want to take the intersection of these two things and say, well, actually, this is the reachable complex from a particular state. That it has a structure that we understand, that is, it's a reachable complex from a particular state where we allow one process to go first. So we'll show the inclusion in one direction first.
You mean both directions?
Yeah, we need to do both directions. The, neither one is particularly hard, but I'm going to do both directions just for completeness. After you've seen this kind of argument a couple times, it'll be pretty easy. So for every execution, so if we start out in S, we let J go first. For every execution where J goes first, it's equivalent to one where we put J first, where J actually does go first. Now, for every execution in the intersection here, we know because X sub I doesn't conflict by hypothesis that it commutes with every earlier operation. So we can pull X sub I first. So it says that this execution is also equivalent to one where X sub I happened, then X sub J, and then E sharp, and then some other execution happened. And that gives us the inclusion this way.
How do you know that there is an execution of I?
Here, P sub I is in this set of pending operations. So if we allow P sub I to take we know that P sub I wants to do something in this state. And so if we let it go first and then look at all the executions.
That's the assumption on the previous slide.
Yeah. Okay, other direction. Well, so for every execution here, what does this mean? Well, it means we let Xi go first, and then we let Xj go first, and then we have a some kind of extension. So we know that E is in a P sub I of S. It's also true that because of these things don't conflict with each other, we can order them. We can change the order. And that gives us this direction. So what we have here is that this is contained in that, which is what we wanted to show. So the actual lemma is that if we have a whole set of things going on here, P sub U, and we have S, then we want to say, well, given our hypothesis that Xi doesn't conflict with anything, we can push the system into state S sub I, remove I from the set of pending operations, and that's the reachable complex, which is sort of what we did when we were talking about the read intersections. We're saying the intersection of these two things is actually the reachable complex from a future state.
What if I wants to write and then read?
Oh, we don't care what it does after that. So if I wants to write and read, that's okay, because it does a write. And then that's sort of implicit in the reachable complex. All the things that it might read will show up later in the extension.
Say we want to read and then write, but the read doesn't conflict, but the write doesn't.
We don't care. All we care about is what happens in this particular state. So what we're saying is that in this state, these reachable complexes, if the very next thing that happens is I or J taking a step. And then whatever the effect of doing that later write is sort of is implicit in the range of future executions, which is the reachable complex. Yeah, yeah.
So now,
But once you...
I want to do two things.
you can only do one thing. So you probably want to do a lot of things. You have a big, long program. And all I'm saying is that if you take the next step, then that pushes the state of the protocol into another state, and then there's a whole reachable complex, kind of a cone.
It might be the case that the next step is also something that I should do.
But it's being an asynchronous scheduler, you might not get a chance to do your second step for a long time. So I can't do two things atomically. All I can do is I can do one next step, and then after that, the scheduler decides when you get a chance to take your next step.
But this, I don't understand what's the U minus I.
Oh, well, it says that if here, I'm looking at this step where I already took a step.
I did one step.
I did one step. And then I'm saying, take P sub j for everything that's in U minus I. Look at the reachable complex starting from S sub I, where j takes the next step, where j is something else in here.
But why can you assume the next step is not also I?
Oh, because the definition of P sub u is the intersection of all the P sub k's, where k is an element of u. So I'm not looking at what happens if I let I take another step. All I'm doing is I'm saying I have this set u, and all I care about is the intersection of what can happen when only those are allowed to take the next step. So so P sub u is the intersection for j and u of P sub j. And so P sub u minus some I is the intersection of a j in u minus I of P sub j. There's an s. So what I'm saying what I mean when I throw this out is I'm saying I'm going to look at what happens if in all executions where the next process to take a step is taken from here. And all the executions where somebody else takes a step aren't represented. So I'm only looking at a subset of the possible executions, which is a subcomplex of the protocol complex. These are things that could have started. So these.
Let's say we had three processes. We threw away three, and now we have we threw away 2 or 0. I said we threw away 0.
Mm-hmm.
So I is 0, and u minus I is now 1 and 2.
1 and 2. So
what is the meaning of the intersection of 1 and 2?
So P sub 1 is everything that can happen if P takes the next step.
Okay.
So these are all the views that are compatible with P sub 1 taking the next step.
Okay. So
And
the executions these are the final steps.
Yeah.
Happening
Yeah. So the final states are slightly ambiguous about what actually happened,
Okay.
which is the essence of all of these proofs. Yeah. And so there could be an execution where I went first, that's indistinguishable, where the execution where 1 went first, which is indistinguishable to one where 2 actually went first. And they both give you the same complex at the end because everybody sees the same view. And so that particular simplex would lie in the intersection of P sub 1 and P sub 2 because it's operationally it's indistinguishable. And when you just do the combinatorics, that's what pops out of the intersection. Okay, so here, so I want to prove this. We just showed that this holds. And so all we need to do is we just intersect over all the j's, and we get these two things on each side. Well, what is this? Well, this is defined to be this complex. This is, we intersect over everything but I, and then we intersect in I, so we get a P sub u of s.
You're assuming that I is non-conflicting?
Yes, yeah. This is case 1. We'll get to case 2 when it conflicts.
It has to be non-conflicting with every j.
Yeah, so this is in the case where we're non-conflicting. So the what we want to say is that if all the operations in U are non-conflicting, then P sub U of S, you know, because we want to do the nerve lemma, we want to look at all the possible intersections of the P sub I. And if you happen to choose a U where there are no conflicting operations, then what you get is that this is equivalent to the protocol complex from some future state, where we basically let everything run in any order we want because they're non-conflicting, and you can't tell what order they run in. And then, so we can, you know, we're going to be able to.
This S prime with this.
Well, S prime is it's a future state we construct basically by letting everything run. But all we need here is that it's just a future state, because the way we'll set up the induction will take care of that. We're going to be inducting backwards in time. So okay. So you know, and actually the you know, we do this. We know that this is true, so we just induct on the number of operations.
The operations are not in U because U was process indices. All the operations,
But there, yeah.
all of the processes in U.
Yeah. So there's, but each one has a unique pending operation in the state.
Yeah, but U formally is a set of
Process IDs,
process
yeah.
IDs, not operations.
Yeah. But I'm mixing the two together just to keep the notation from getting too crazy. But that's, but you're right. U is a set of process IDs. Okay, so that was case one. Case two is
Case 3?
no. The you know, so case two is pretty similar, and so you know, I'll go through it, but you've already done most of the hard work. You know, so here, what happens is if it conflicts, then you know, so PI has a read. You know, if there's a conflict, it's a read and a write. We're going to pick the reader. P sub I is the reader, and J is about to write to that location. So what I claim here is that now we're going to look at the intersection of these two things. What is this? Well, we start in the same state, but we look at a different protocol, one where I doesn't participate. So in particular, if we induct based on the number of processes, then we'll have. Yeah. So we'll have one induction based on time and one induction based on the dimension, depending on whether it's conflicting or non-conflicting. So this is the reachable complex from S if Pj goes first and Pi does not participate. So superscript means you don't participate. Subscript means you go first. So we want to do inclusion in one direction. Here, if E is in Pj, then that's equivalent to doing a write first. So Pi reads the new value. If we look in the other direction, if E is in P sub I, then the read goes first, so Pi reads U. So if you're in here, Pi sees one thing. If it's there, it does something else. So that means there's no execution where P sub I has a vertex. P sub I has no vertex in the intersection because it can't see contradictory things. So that just means that it has to fail before writing, and if it fails before writing, it may as well fail before reading, because it's kind of a black hole. It's not going to release any information. So that says that the intersection of these two things is contained in here. The other way is basically the same trick. Is we can write this as here I fails, J goes first. We say, well, I goes first, but it fails before it writes. So E is in, so this execution is in P sub J of S because it fails and we can throw it out. The other direction, E is in there. The fact that E is in P sub J means we put the write first and the read afterwards, and so on. So what we get out of this is that is the inclusion going the other way. You know, so this is.
So the first direction depended on this being a full information protocol here.
Yeah.
Independent of that.
Yeah. I think if you well, actually, it depends on the fact that they're writing different things. You know, if they're writing, if J was writing the same thing that it wrote before, then this wouldn't be true. But then, but we don't want to deal with that, so we assume that everything you write is unique at least. So then, so the claim here that we want to show is that the intersection of these things is a smaller intersection of a smaller protocol. That is, the reader that has a pending conflict, it's unambiguous whether it went first or it didn't, so we have to kill it. And if we kill it, then it is ambiguous whether it went first, because it could have gone first, and then but it never told anyone. So you know, we just showed this. By taking the same trick, we take intersections all over the place, and we get this property. So what we want to show is that if they're, oh, this should be conflicting, not non-conflicting. This is another bug. So what happens is that this is equivalent to taking some state S prime, some collection of processes that fail where M lies between this number and that number. So it's a smaller number of processes in a smaller set. But it's still the execution of a full read-write protocol from some state, just with fewer participants. So we just do induction. You know, we prove this, we do induction. So, you know, that's all, you know, it's not very exciting, but it shows that, you know, we really, in order to, this is all the model-specific reasoning, but we've managed to bottle it up into one statement about the connectivity of the protocol complex. So it doesn't, you know, run all the way through the proof. You know, if you wanted, if I throw it in test and set and want to prove it something like that, then that would go, you know, then there would be another slide looking at another case. Mercifully, there isn't, but this is, you know, this is the sort of clean division between the model-specific arguments and the more general arguments. Okay, so corollaries for all states S, P of U, this is non-empty because it represents the execution of a protocol either, you know, with fewer participants or with, or from a later state. Because this is non-empty, it means the nerve complex is simply an n-simplex. So what is this? This is the intersection. This is actually a simplex of the nerve. You know, this is each piece of I is a vertex of the nerve. Each piece of U is the intersection of these reachable complexes, and it's a simplex of the nerve. So the nerve complex from any state has a nice simple structure. It's an n-simplex. So the main theorem is if P is a read-write protocol, I want to show that this is, if you start off from sigma, that you're connected to the dimension of sigma, which is enough to show that n set agreement is impossible by the previous argument. So at this point, we're ready to put everything together. And all of those, you know, somewhat tedious lemmas and so on are going to be rolled out like some, you know, Wagnerian opera, and we'll do the grand finale of the proof. And so the key observation is that n connectivity has a critical state C. That in the final state of the protocol is a single simplex. Single simplex is n connected. So the reachable complex is eventually going to be n connected. Let's assume by way of contradiction it isn't n-connected when we start. So that means that it must have, if you have something that is true in every final state, not true in the initial state, then it must have a critical state where the reachable complex is not n-connected, but the reachable complex from every successor state is n-connected. So it looks like this. Here's our critical state. Here is the reachable complex. This is covered by the P sub I because somebody has to go first. Those are the only possibilities. And so the reachable complex from C is the union of all of these. So we have a covering. P sub C is not itself n-connected, but each component is n-connected because it's a critical state. So you can see how we're sort of rolling in the nerve lemma here. And what we need to show is that each P sub U is n minus U plus 1 connected. And if that holds, then we know that the conductivity of this thing depends on the conductivity of the nerve, but the nerve is trivially n-connected, so we'll be done. So what we want to show is that this is n minus u plus 1 connected. There should be an absolute value sign on the u here. So we'll argue by double induction, first induction on n, the number of processes. Base case, when n equals 0, we're saying we're looking at weight-free executions of a single process. You know, it's deterministic. You know, the entire complex is a single vertex. So, that's easy. That was easy. So if u consists entirely of non-conflicting operations, then we showed that the P of u of c is just P of s, where s is some state that's reachable from c. But c is a critical state for n connectivity, so the protocol complex from any reachable state has got to be connected. It's got to be n connected by the hypothesis that c is a critical state for this property. So you know, that's that case. If u has conflicting operations, that's the other case, then we know that this is equivalent to p prime of s, where s is an m process protocol for strictly fewer processes. And so by induction hypothesis for n, we know that this is connected. So now we apply the nerve lemma. So each p sub u is n minus size of u plus 1 connected. So that says that P of c is n-connected if and only if the nerve is n-connected. But we've already seen that it's connected, and so P of c is connected. But by hypothesis, it wasn't. So that's a contradiction. So the only way we can resolve this is to say, well, n-connectivity is eventually true, but it doesn't have a critical state. Therefore, it must have been true at the very beginning. So no matter you know, how you start, the reachable complex must be n-connected. So what we did here is I gave you, first off, model-independent topological properties that prevent consensus, and that was path connectivity. If your protocol complex is path connected, you can't do a consensus. We prevented k-set agreement by doing k-connectivity. And let me emphasize that this is a more general case of this. You know, I could have just proved this and derive that as a corollary, but that would be kind of cruel. So then what we did was we did model-specific applications to weight-free read-write memory. First we showed it was path-connected. Then we showed it was n-connected. But here too, the n-connected proof implies the path-connected proof. Although in each case, you know, the path-connected proof is you could do in 3 slides. So this one required more like a dozen slides. But in some sense, it's a direct generalization of the earlier argument, you know, where we reason about the pieces, we glue the pieces together, we reason about the intersections, and then we apply the nerve lemma. Okay, so that's it for connectivity. What I'm going to do next time is I'm going to talk about what we'll call colorless tasks, which are a slight restriction of tasks which have a very nice, which are relatively easier to deal with. Later on, we'll talk about colored tasks, which are require a little bit more machinery. So we're going to follow the same pattern we did before, where first we talk about manifolds, get some results out of that, and say, well, actually, not everything is a manifold. And then we talk about connectivity as a generalization of this. Next, we'll talk about colorless tasks, and then further on down the road, we'll talk about colored tasks as a generalization of the earlier ones. So, you know, the material in this course is, you know, like boiling a frog. You know, we're slowly going to bring up the temperature, and if we do it slowly enough, I'm hoping no one will notice. So we'll see you next week.